before we move on? Anything I can help with?
I don't, but I'm not sure about anybody else.
Well, if you got something, just shoot. All right, so we only got 3 people in here. Um, the fellow that runs basically the math person for the West Bank campus. He said he was going to stream this on the board, uh, so hopefully people showed up. Did y'all see my message about this? I sent an announcement, but I know not everybody checks their email. And then, did y'all get an announcement?
I see the announcement, but I
Well,
just got on.
and it sends it out to your default email. And the problem with that is, I think students don't quite understand the email. I mean, I had a student last week. I mean, I'm talking about a good student. She still hasn't been in her email, and she was wondering why she couldn't get on the Wi-Fi, and it's because you got to get in there and handle. You initially change your password and all that, and then you can get on. And I don't know why. I say this. So if you can't, unless you happen to come into Canvas and see that announcement, I mean, you're not getting it, checking it in an email, and I sent it out yesterday. So hopefully we'll get a few more people. But I got a feeling that there might be a couple of people out there. If you are out there, just send me a text or an email saying that you were in class. I'll take your word for it. All right. Now, last time we talked about um, these things called rational inequalities. And it's important to understand what this means and the relationship between 3.5, which was actually graphing the um, the functions themselves, not the inequalities, but the functions. But there's a nice relationship here that can help you understand how the graph works if you can follow what I'm saying. And what I was going to do is one more problem from 3.6 that's an application. So we'll go through the whole process. It's just that and then when I'm finished, I'm going to show you a graph, and hopefully you'll be able to see how this solution set relates to the graph and can help you know what the graph looks like. All right. We had talked about it a little bit before, but here was one we went through briefly. What you have to do when you're talking about if you have a rational expression like this one here, 2x over x plus 1 is greater than or equal to 1. We can't do anything to this until we get it greater than or equal to 0. And what they had done was just find a common denominator over here. That's what that whole process is. Put it all over the common denominator of x plus 1, and then it was set equal to greater than or equal to 0, which is what we want. And what that tells you by looking at this, it gives you two of these points that are checkpoints. Now they call them boundary points in here, but it's the same thing. So if we solve this one for 0, we get x is equal to -1. If we solve the one up there, we get x is equal to 1. All right. And so 1 and -1 are our boundary points. So -1 and 1. Now they draw in a dot there. I think that's kind of bad. I probably would just put a line because there's still a little bit of confusion from people probably from high school days that you use the filled in dot to mean the bracket and the parentheses to mean the circle. But that's not what these dots mean. It just represents that's how we're breaking it up into 3 points. I'm sorry, 3 parts. We got this section over here, negative infinity, -1. And then we got -1 to 1, and we got 1 greater than infinity. So there's 3 points. So we got to check 3 different parts. All right. So what they do is, now notice that the number over here, -2, is the very next one. Um, that is just the obvious one to pick. Of course, you don't necessarily don't want to pick any fractions unless you like working with them. But anyway, and then they're going to pick 0 in here in between that one, and over here they'll probably pick 2 if I remember, because we kind of went through this. But I just wanted to refresh. So when you put in -2, you come out with a value of 3, which is positive. Now that means that that whole section of graph from infinity to a -1 is going to evaluate greater than 0. So that's part of the solution set. And then when we do 0, it comes out to a -1. So that one is less than 0. So anything between -1 and 1 is going to be not part of the solution set. And then this one was positive. Okay. So it flip flop back and forth. Sometimes they do that, but not always. So let me show you something with the graphing. I like the little graphing thing that I use, Desmos. Let's see, it was x minus 1, x plus 1. All right. So just kind of notice. Let's see. I'm going to put in the points that they had. Let's see. It was 0, -1. No, I'm sorry. It's -1, 0. Okay. And what that is, that's the asymptote. Okay. So that's why that was a boundary point. And then this one is another boundary point. All right. So what do you notice? And let me just kind of put a line. All right. So remember, it said that this was part of the solution on that. So this is how you draw it. That means that a negative infinity to -1, they got it messed up. They should have a -1 there. And then that's part of the solution. And they got a parentheses because it can't be -1. All right. So what do you notice? And this is very simple. It's not a complicated question. I'm not trying to trick you. What do you notice about everything all the way to the left up to -1? It's what's its relationship to the x-axis? It's positive. It's above the x-axis. Well, that's what this whole thing was about. That's what we were essentially checking. So notice also that this part from -1 to 1, this is where we check 0, everything down there is negative. Okay. And then everything to the east of 1 is also above. So when you're talking about what the graph looks like, and this is why 2.7 can help you with graphs if you still need some kind of picture of things, is that it tells us when it's positive that it is above the x-axis. In other words, the functional value, y value, is positive. All right, I see he's got us logged in over there, Lab Podium. He's going above and beyond to Call of Duty there. I never would have thought of doing that. So like I said, it's because I'm afraid that some people showed up and they're sitting there in the room.
Hey, Mike,
Yeah.
I got a couple of people in this class, so I'm gonna take their names, okay?
Okay, thanks.
All
Yeah,
right.
I figured there would be because there's several people that are loyal that are showing up in class. And like I said, is even the good students, they don't always check their email or they don't know how.
Yeah, okay, well, they're here. I'm gonna just sign a paper. All right.
Okay, thanks. All right. So now let's look at an application for this section and see what this method entails about what the nature of the inequality is, and then I'm going to show you the relationship to the graph. All right, so we've got, and this is just a general function. It's about position is equal to negative 16 t squared plus VO can be of any coefficient of t plus another, just constant term there. And all that tells us that's the general equation or function for a projected item. It could be a rocket ship, it could be, a missile, it could be a mortar, it could be a baseball. Anything that goes up in the air is going to reach a vertex, a high point, a maximum, and then it's going to come back down, and you're going to have a certain level of symmetry associated with it. All right. So now they're going to give us some information here, information that we can use. An object is propelled straight up from ground level with an initial velocity of 80 feet per second. Its height, time t, t is the time, and then the s of t is just where it's at as far as, what is it? It's feet, right? Yeah, feet. So s of t is equal to negative 16 squared, and 80 is the initial velocity. Like if it's being shot up, it's going to have a certain amount of speed associated with it, so it will affect it. So that right there is the velocity. Now we don't have to do anything with this other than answer this question: at which time will the object be more than 64 feet above the ground? Now they gave us three things. They gave us the equation, they plugged in the 84s, and then they tell us that 64 is the height we want to reach and find out when this thing is above 64 feet. So then what do we do? Well, we just turn this into an inequality where it's negative 16t squared plus 18t is greater than 64. But remember, for any of these, we got to have them with 0 on the one side. So what that means is we're going to subtract 64. Okay. And then there is that function that we're going to treat it now as if it's an equation, and we're going to solve it and find out where our points are at for the boundaries. Now, this is just a little bit of wisdom. It sometimes takes a while to learn this, but anytime you have a greatest common factor in an equation, especially with a quadratic or any kind of polynomial, you want to factor that out. All right. In this case, negative 16 is common to all of these terms. But what we're looking for the zeros of that function, which is going to be our boundary values. So all we need to be worried about is t squared minus 5t plus 4 is equal to 0, because the negative 16 doesn't have a variable in it, so it doesn't, it doesn't give us anything. We're just holding it over there because technically it is part of the factoring. Then we set t minus 1 is equal to 0, and t minus 4 is equal to 0. So t is equal to 1, t is equal to 4. All right. Now, what they're going to do is, for this one, they're going to check a point between 0. Hold on a second. 0 and 1. Oh, I'm sorry. Okay. 1 and 4. There's only 2. I was a little bit taken aback a minute. So we can check 0 over here. We can check 2 here, and we can check 5 here. All right. Now, to just make this quick, I may already have this done over here because I was doing it a little bit earlier. So there's your boundary points. And for some reason I did half for some reason. Okay, so when you put in 0, it comes out to negative 64, which is what they tell us. All right, it's negative right here. All right. So in the middle, 2, if we do 2, I'm sorry, if we do, yeah, 2, that's this one here, it's positive. And then on the other side, 5, and that's negative. Now, what does that tell us? Well, that tells us during this segment, from here to here, that's the only one that gave us the positive. So everything in that range is positive, and therefore, what do you think the graph looks like? Well, let me show you. And hopefully this will give you some insight into what, and I got to put X because it doesn't like T. All right. So notice, again, it's a parabola. It's going to go pretty high, so it's kind of hard to see it. But look, all of this between 1 and 4 is positive. The functional value is above 0. So that's what this thing told us. And so I just wanted to relate it to the graph because in addition to it being able to solve an application, you can relate it to the graph. And like I said, is if you're not sure about the function of the graph, you can tell the boundaries on which that graph is above 0. Okay, any questions? All right. Let's look at now the 3.1. The 3.1 is a little bit, this one's actually not too bad. The logarithmic is a little bit harder because you got to work backwards. And the way that it works in math is you have a whole host of operations and they have an inverse. Like, for example, addition and subtraction are inverse operations. They undo one another. Multiplication and division are inverse operations. They undo one another. The square and the square root are inverse operations. They undo one another. Likewise, are the exponent and the logarithmic functions are opposites of one another. Okay, they undo one another. All right, so an exponential function is just one that looks like this. It doesn't necessarily have to be f of x equals b to the x power. It could be y to the bx. B being the base and x is the exponent. It's got to be greater than 0 and not 1. And we just kind of, and x can be any real number. So that's just the limitations on it. All right. So let's just look at one of these. We're just going to evaluate it. And like I said, I got another one or two I can do after we go through these examples because I like these because they're nice and typed out and easy. And then you can see the explanation. And then we'll just take a couple I'll pull from the back of the book and go through. All right. We got an exponential function f of x is equal to 42.2 x. Where did they give the function at? Oh, I guess I don't. 42.2 and then 1.56 to X models the average amount spent in dollars at a shopping mall after 6 hours. So there's no explanation on where they got it at. They're just telling us that. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? Okay. Remember, 0 is time, is the beginning time. So 1, 2, 3, the number 3 would be what you're going to put in for your X. And so if you take 1.53 to the third power, I'm not sure if I can do it on this thing or not. I'm not really a fan of these TI calculators, but I was just going to show you. Technically, you're not supposed to be using this. That's right. And I don't have one virtual like you've got. Let's see. So 3.749 times 42.2, and that's gives us 160.21. And so after 3 hours at a shopping mall, the average amount spent is going to be $167. I'm sorry, $160. Okay, pretty straightforward. All right. So let's just look at an exponential function, and let's see how we might graph it. You remember from the very beginning of graphing, we just kind of pick points, and usually it's wise to pick points around zero and work our way out. But anyway, if we have f of x is equal to 3 to the x power, in other words, however many times x is, that's how many times we're going to multiply 3. So starting down here with the easy one, f of 1 is equal to 3 to the 1, which is equal to 3. So that's that point right there. Now, if we put 0 in, and hopefully by now you realize that any number you take to the 0 power is always going to give you 1. So what's always going to happen with these exponential functions is they're going to go through that point, 1 or 0, 1. They're always going to go through that because any base taken to the 0 power is 1. And then working on the other side, the -1, all that does is give us the reciprocal. So it's just a little piece of 1/3 in between the x-axis and 1. And then f to the -2 is going to be 1/9 because the -9 results in a reciprocal, and then we just square when it's in the denominator. So notice that what is happening is that the x-axis is an asymptote, horizontal asymptote, so it's getting closer and closer and closer to that value. It'll never get there. If you were to take, for example, I'm going to use that one. This is sort of like the one that's built into Canvas. I'm sorry, not Canvas, into my math lab. But let's just say we would take 3, and we're going to take it to the 50th. Oops. 3, and we're going to take it to the 50th power. Look at how big that gets. Wait a minute. Well, let me back up. So if we had x equal to 50, it's going to be way up there. But I meant to put in a -50. Well, I'm going to put something smaller now. So it was 3. Let's just say -8. Well, I must have done something right. I think I'm going to have to use a parentheses. Oops. No, I've done it. Okay, I think I got it. 3. I got 2 of them in there. That's not going to do it. I guess what I got to do is do a parentheses. Oh, and 2, that's not a, I forgot. You got to use this. All right, okay. I'm just going to use the Desmos. It's easier. So if we go here, we're going to put 3. And let's just say we got -8. And I'm going to put an equal sign. Oh, it was 3. I'm sorry. The one thing you got to worry about with computers is they all, okay, there it is. See how small that is? 0.000015. So finally got it. So this thing, as you get over here, so in other words, when we get to 8 negative, it's going to be even closer. But it's, again, it's an asymptote, and it's never going to get there. Okay? It's just going to get closer and closer and closer, and always just a little bit closer, but never touch. Now, for transformations, all right, we're just looking at these same points here. All right. So there was negative 1 1/3, 1 and 3, and 0 and 1. All right. And then the asymptote was 0 for y. Okay, but let's say we want to graph this one. Now it's in the parentheses, I'm sorry, it's in the exponent. So that's going to involve the left-right shift, okay? This is equivalent to it being inside of the function. All right, so notice the red one was the original one, right? Well, they changed it to from black to, no, the black is still it, okay. So there's that point. It was a negative 1 1/3. Well, what happens is that it got shifted. What was it? It was 1 to the positive direction because it was x minus 1 up there. Okay. So that means positive direction shift. So now there's our shift of 1 right there from the y-axis to x is equal to 1, or from x is equal to 0 to x is equal to 1. That's our shift from 1. All the points are the same except for the adding onto the x value. In other words, when we add 1 to negative 1, we get 0, and we still get 1/3. Same thing with this one. We still got, if we add 1 to 0, we get 1, and the y value changes the same. There was no y shift. So here again, we add 1 to x, it gets us to 2, and the 3 stays the same. And again, remember, that's considered inside of the function. So that's why it moves to the positive side of 1 rather than the negative side. You just got to remember, anytime you're working inside of the function, or you're working with the x, essentially, you're jimmying with that, it goes just the opposite of the sign. And if we'd had x plus 1, then we got to look at it as x minus 1, or x minus a minus 1. So it works just the opposite. All right, so basically it's a function, so the domain is all real numbers. For the range, you're always going to be positive. All of them pass through 0, 1 because of that fact that if you take any function to the 0 power, it's 1. Now, if the b, in other words, the base is greater than 1, and in other words, if it's anything above 1, if it's positive, but non-fractional, because anything between 0 and 1 is going to be fractional. But anyway, when it's greater than 1, then it's an increasing function from left or right to it's an increasing function. And the greater the value b, it's going to increase at a more rapid rate, because if you got 10 as your base and you take it to the 10th power, it's going to be 100. But if you have 2, it would only be 4. And in between, in other words, if it's 0 and 1, in other words, if it's a fraction amount, then it's turned around. And that's just because of the nature of the way fractions work, we'll see. And this is a 1-to-1, and it has an inverse. We're going to see the inverse as the logarithmic function in the next section. And then it approaches, but does not touch the x-axis. In other words, y is equal to 0 is the horizontal asymptote. All right. All right, so let's look at this thing called the natural logarithm. Well, it's the natural exponent, and then we'll see that there's a one called the natural logarithm. That's the inverse. But base e is defined as this, and it's in a crazy way: 1 plus 1 over n to the nth power. And what that essentially means is that you're never going to have it's the value of e is what we would call an irrational number. It never repeats. But what people have found that studied this is that it mimics a lot of processes that go on in nature. Like one of the things I think is like radioactive decay, or just any kind of decay. You can use it for different kind of things. Like one of the ones I used to think remember was like if you have somebody that died, you can find out when they died by measuring the temperature and then using an equation to that uses the natural exponent to judge when they died, because at that point their body would have started cooling. But there's other applications, and we'll see. All right. So generally, you kind of, unless you're, you can look at it as just 2.72, but pay attention to any kind of instructions that mentions rounding, because the rounding is important. Because if you want to round off, and I used to run into this problem a lot in statistics, because statistics is almost always approximations that you have to, because none of your values, or very few of your values, are going to come out to anything whole number. So what you have to do is if you want to round to the 100th spot, you really, in your initial calculations, go 1 or 2 beyond that, and you don't round off until the end, because once you sacrifice your accuracy, you can never get it back. So you got to continue having a higher level of accuracy than what you want to round off to. Okay. So just keep that in mind. If it says use 2.72, like I said, then I would use 2.72, and then maybe in my calculations go 1 or 2 beyond that, and at the end round off to what they want. All right, so this thing's called the natural exponential function. All right, so they give us an exponential function, and it's f of x is equal to 1145 e 0.0325x, models the gray wolf population of the Western Great Lakes, X years after 1978. Project the gray wolf's population in the recovery area in 2017. Now, as I had said, is these things with the natural, they're to mimic things that happen in nature. And one of the things that, like I said, there's decay and there's growth. Both of those use the E. So in this case, we don't know whether it's they don't tell us whether whether they're going to be more or less, but we're going to find out. All right, so if we want to have 217, then what we got to do is remember the starting point is 1978. So you don't want to just stick 217 in there. Year 0 would be 1978. So what we're going to do is find the relationship, and that's 39 years after 1978. So what we want to use is x is equal to 39. All right. So we got that function and we put in the 39. Let's see if I can do this. All right. So that's going to be the exponent. Let me store it somewhere here. Should be able to do that. All right. So we're going to do I see 11. I'll tell you what. So we'll do the exponent first. So that's 3.55. In other words, the E part is that, and then we're going to multiply times 1145, and you'll see that we get 4,066.99, which is approximately 4,067 wolves that you could plan on being there in that Great Lakes area. All right, any questions? All right, another kind of example is one with interest. There's a thing called compound interest. Um, I don't really think about this so much because the interest rates are so low that people don't generally do this much anymore. Go sit around and worry about what the interest rate is and how fast the money is going to accumulate. But this would tell you that. Now, the first one is the amount that you would have is equal to the principal, however much you stuck in that account, times 1 plus R is the rate. Okay, no problem, William. I don't consider you might be around somewhere. All right. And then the N is the number of compounding periods. You know, if you've ever seen things, they might say compounded quarterly. Um, you could say compounded 6 times per year, or 12 could be every month. And then for continuous compounding, in other words, they kind of calculate as they go, you use a little different function. All right. So a sum of $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years subject to quarterly compounding. So quarterly means 4 times. Okay, so N is going to be 4. We've got the rate. Now, remember, um, generally speaking, mathematically, you don't work with the percent. You have to use a decimal. So what we're going to do is move decimal over 2, so we got 0.08. So that's where that comes from. So we replace the R, the rate of interest, with 0.08. We replace the N with the number of times we're going to compound. And then we close off our parentheses, and we're multiplying 4 for the number of compounding periods times how long it's going to be in the system. In other words, or be in the account. So that's 4 times 5. So again, I'll see if I can do it on here. Just to show you. So remember, 4 times 5 is going to be 20. So when I use that at the end, you know where I got it. Okay, so it's 1 plus, I'll tell you what, I'm going to kind of go backwards. I'm going to do the 0.08 divided by 4 plus 1. And then I'm going to take that and I'm going to raise it to the 20th power. And then I'm going to multiply it times the principal. So we get 14,859.47. So over 10 years, $14,859.47. And you'll notice that before I multiplied by 10,000, I came up with that inside. It was 1.4895, 1.48595. Anyway, that was about what you could expect the growth. In other words, you're going to have almost 1.5 times what you started with. It's not quite, but close. It's not quite. If it had been 15,000, it would be 1.5 times, but it wasn't quite that amount. All right. So compound interest, how can we deal with that? Hold on a second. I was just going to make sure we had another. I was going to go through another problem. I want to make sure I had it ready. All right. So this is the one that's, I always like to look at that and just read it PERT, kind of help me remember it. P E to the RT. So again, we still got a principal of 10,000. The E is built in, and then we're going to do, it's at 5 years this time, and it's 0.08. So let's look at this. Just let me show you that we can do these things. All right, so it's 0.08 times 5. And we'll stick it in my memory. And then I'm going to do E. So 15 points. So that's a little over. Let's see. Hold on a second. I think I had something in still in the memory. So it was 0.08 times 5. Okay, so that's 0.4. And then we're going to take E. And see, that's the 1.49 times. Again, it's closer to 1.5 than the other one. And then we're going to multiply it times 10,000, our principal. And that's where we get $14,918.25. And of course, the compounding continuously offers more, more, a greater amount, because it's, you're not having to wait in order to compound. Like when you're talking about working over a certain of like quarterly, you're essentially going a whole 3 months before you're compounding. So certain things aren't getting taken into account. So you're going to end up with less. All right, let's just look at a few more problems from this book, kind of by scratch. Kind of from scratch. And then might start a little bit of 3.2 if we got time. I just don't want to rush that next time, but it might be all right. It's just a little bit longer than this. So probably gonna have enough time. All right. All right, let's just say we want to graph this thing. And we got g of x, and this is from the textbook, like the back of the actual ebook. All right, so just to do a little t-table like they do. So if we put in 0, that's going to give us 1, because anything to the 0 power is 1. If we put in 1, well, that's going to give us just the same thing as b. It's 4/3. Now, let's just say I do -1. What happens? Well, it's negative, so it ends up turning it into a 3/4. That's all it does. And then we'll just do 2 more. Do 2 and -2. All right, so if we do g of 2, we get this, which is 4 squared over 3 squared. So this is 16/9. All right. Now, what do you think is going to happen with the -2? The only thing that's different is the negative sign, and that's basically reciprocal, but I'll take you through it. Well, the first thing to do to get rid of the negative sign is we take the reciprocal. Reciprocal bond, this means the negative sign in the exponent means take the reciprocal. So it's still squared. So now it's 3 squared over 4 squared, which is equal to 9/16. So it's just the reciprocal of that. All right. So let's go back over here and I'm going to plot those points on here. Okay. Oh, wait a second. It's not, it's 4/3. How did I get that? Oops. I'm sorry, it's 3/4. And this one's a 4/3. And then the 2 is going to give us 16/9. And then the -2 will give us the reciprocal of that. All right, now you can kind of see what's happening here. And then if I just throw that in there, the function. Now, one of the things, and just to harken back to 2.7, what we just finished, all of this is positive. So if you were to somehow found boundary points on that one, I'm not sure you can, because it doesn't change. The whole range is going to be above. This will always be positive. Yeah, there wouldn't be any boundary points, but if you put any value in for the function, it's always going to be positive. So, oops, what happened with that? Oops. So that goes right through this point. So all of the exponential functions look like that for the most part. They might be a little bit different, but they all go through 0, 1, and then you find some other points by just picking anything. All right, let's look at a little shifting. just briefly. We looked at one that had a horizontal shift. Let's look at one that's got both. All right, let's say we've got all right. Now, if we want to add a 2 to the x, in other words, 2 to the x squared, what that's going to do is it's going to be a negative 2 shift to the left. So watch. Oops. Okay. See that? It shifted over. Now, let's just say we did a shift like that, which is the up and down shift. Notice the red one comes down 1 because this is 1 right here. You know, no matter what we do. So if we did a +1, it would go up. All right. If we do a -1, it comes down. All of that's still the same. The best place to look is to look at that point right there and what happens to it. See, that's the down. This one shifted over to the left. So if we put in both of them, you're going to have this one and it's going to be down 1. So let's put both of them together. All right. So it puts together both of them. So the shift, what you could kind of think of this is sort of like for a parabola, you had a vertex or you had some kind of point that you could kind of look at. And in this case, when we're dealing with the 0, 1, that's the one that's getting shifted. So it shifted over for the x plus 2. I'm sorry, yeah, 2. From there to the -2. And then the -1 means going down. So it's down from that original one. So right there, 1. Well, actually, here's a better place to look at that one I was telling you about. Look at that one. All right. Y'all doing okay out there?
Yes.
All right. There was a problem, and I need to bring up the book to kind of show you because there's a chart in it, and I'd picked this out. So I really need to have the book open. I wish there was a way. They don't like you to just take the book and have a PDF of it. I remember one time you could do that, and then you could just print the whole thing out, and then it was just like how it used to be when you had paper textbooks that you didn't necessarily have to buy one. And then they, of course, stopped doing that. I don't know why they would. You can't go back to that because of the fact that they're still charging you a subscription price. This was a little bit different, but I wanted to look at it because it just as a comparison. It's kind of one of the harder problems because it's in the back of the, way in the back of the problem sets, but it's really not that hard. All right. Oh, and this is just kind of neat. You remember they showed you that 1 plus 1 over n to the nth power would basically give you um, the value of E. Well, this is how it's gotten. They get it because the higher the value you put in for the N, the closer it gets to the actual value. It's what we call a limit, essentially. It just gets closer and closer the higher you get on your X input. There's the gray wolf thing. All right. Compounding we looked at. Well, let's look at something that's a little bit different. All right. So we're looking at this chart right here. Okay. Not exactly at the moment, but this is what we're going to do. They say that this data can be modeled with either this one, which is a linear function, x plus 31, and then you can also use an exponential one, 32.7e. And what they ask us to do is calculate it both ways and then see which one's better. Because what they want us to do is look back at the chart. So let's go over to that board. All right. Some of these things that I necessarily want to erase. I don't know why. But anyway. So okay. Now we'll just say graph in the book. I thought there was a page number somewhere. Anyway. All right. So we got f of x plus 31. And then we got g of x is equal to, oh, I forgot to write it down. It's 32.7 0.0217. Okay. All right. What were the instructions to say? I was going to do a 72. So it's 2010. So what we want to do is, according to the linear model, what percent of high school students, and they don't even let you copy this. This is what's got me. All right. If you select to try to copy it, it doesn't have as an option. Plus, I was trying to do it with a keyboard. But anyway, so again, we have to do the same thing with years from 1980. Just remember that. You don't want to just throw in 2010. It starts at 80. So we need x is equal to 30. For the year 2012, for x is equal to 30. All right, well, this one right here is a breeze, right? Okay, 61. So 61% according to this linear model. All right, and the other one is using that g of x. So that's going to be 32.7 0.0217 times 30. All right, let's see if we can get our little calculator to all right, so I'll do the exponent first. 30 times 0.0217. So that should be our exponent. And then, oops, I'm missing the E, I'm sorry. So I'm going to have E. So 1.917 times the 32.7. And that gives us 62.7. Or approximately 63%, we'll just say. All right, so let's go back over there. Which of these is more accurate to the graph? Or more true? All right, let's just go over there and look. For 2010, right here, what is that value?
$61.
Yeah. So which one is closer? Which one of the calculations was closer to 61?
A.
Yeah, A in this case. So it doesn't necessarily mean that the exponential model will be more accurate. It's just that sometimes a linear model fix. 1 second, hold on a second. So what this really shows is that sometimes the linear model might be or another model. It doesn't necessarily have to be linear, but if you take statistics, what we do over there is you kind of find functions that fit data. And we only deal with the linear models over there, but sometimes you can find that linears can be very, very accurate. And then sometimes you need something that's exponential. All right. Let me just hit on a couple of things. We're almost done. I just want to just show you a couple of things about the inverse functions called, or inverse of the exponential is called logarithmic. A logarithmic function undoes what the exponential function does and vice versa. All right. So, B can't be equal to 1, and then Y can be any value, but also X has to be greater than 0. Now, what this is essentially saying is the log of base B X is the way you would read that. Now, what does that mean? Well, it essentially means this. If we get the log of 7X is equal to 3, then what we're looking for on the other side of the equal sign is the exponent that would go with this base. In other words, 7 to the third power would equal to X. And I'm not sure what that is over there. See, 49 times 7, whatever that is. Doesn't really matter at this point. I can't think what exactly it is. And then this right here, the log base B, that's 25. Well, what exponent would I need? Well, the B would have to be squared, because that's on the other side of the equal sign, is the exponent. And this is the base, whatever is there, is equal to 25. So all we're doing is just changing over from logarithmic to exponential. So log 4 of 26. So 4 to what power, because they don't tell us, is equal to 26. And it's probably going to be some, well, I know it'll be some kind of a irrational number, because there's no instance with whole numbers where 4 to any power is 26. If you square 4, it's 16, and then when you cube it, you get 64. So it'd probably be 2 point something. Likewise, if you got 2 to the 5th is equal to whatever, in this case X, that just means log 2, whatever the base is, still call the base when you're talking about logarithms, X is equal to 5. So here we got the base B, so log of B, and then whatever is on the other side of the equal sign when you're dealing with the exponent becomes part of the logarithmic sign, and this is all equal to that power. When you're dealing with a logarithm, you're always looking for that power on the other side of the equal sign. When you're dealing with it like this, you're trying to find out what the final product of this is. But here they're giving you the product as part of the logarithm. All right, we'll just look at this, and that'll probably be enough for today. But this is kind of how it works. If we wanted to evaluate log 10, and when it's 100, in other words, we're going to take the 10, and what power gives us 100? So, well, that's 2. 10, the value of that logarithm is 2, because we're looking for the power that goes with base 10 to get to 100. On this one, base 5 means to what power. We're always looking for what power. If we've got our little product there, gives us 125. Well, 5 cubed is 125, but it's also in the denominator, so it has to be negative. So -3 is the answer to the logarithm, which is the power that we take the base 5 to in order to get 125. So log 36, when does it get to be 6? Well, so log 36, in other words, 36 to what power would give us 6? Well, if you remember back from your 097, when a exponent is rational, that essentially means take that root. So if we take the square root of 36, we get 6. So the square root, the way that it's written as an exponent, is 1 over half. I'm sorry, 1 over 2 or 1/2. All right, last little thing. Now this one, we need 3 to something, that 3 to some power that's going to give us 7th root of 3. Well, this is a pretty easy one because what that is remember, I'll just write it on the board in case you don't remember it. So a to the 1 over n is equal to the nth root of a. So that's where that's coming from. If you can't remember, that's the definition of a rational exponent, is just to take the root of it. 1 over a to the 1 over nth power is the nth root. All right. So in order to get the 3 into to that 7th root, well, we just take 1/7 power. That's all there is to it, because the 1/7 power translates to the 7th root. So we'll take up there. If you got any questions, stick around and we'll start from right here next time, and we should be able to finish up.
Have a good day, Professor.
Okay, bye-bye, Mika. Thanks.